Hi everybody, my name is Sarah. I work at Airbus and I'm here to give you a talk about BinCAT, the static analyzer of binaries that we develop in my company. The content of this talk is as follows. First, I will present a big picture of the talk, then I will show you 2 demos of it, then some internals, and finally I will conclude with the future work. So, let's start. What is BinCAT? It's an analyzer of the executables. It is fully static, which means that the program under analysis is never executed. It deals with several architecture. For that, it translates native instructions into a set of statements which are actually analyzed. And it is based on a theory, a mathematical theory called abstract interpretation, which makes it an extensible framework. We will see it later. Currently, we have several analyses. We are able to compute values of the memory and the register. We have a taint analysis. We are able to reconstruct control flow graph even in the presence of indirect jumps. We reconstruct high-level types. We detect use after free, double free, and stack overflow. The analysis can be performed forward or backward. And to make it more friendly, it comes with an IDA plugin. Let's start with the first demo. In this demo, BinCAT will analyze the CTF of BlackHoodie 18. It's a typical CTF when you have to diffuse bumps until you get the flag. So let's start. Here you can see IDA, and on the left there are several panels that are for the BinCAT plugin. To start an analysis, you will just select the first instruction you want to start with, and then with the shortcut, you launch it. When it is done, every instruction that has been analyzed is in gray. And here we can see that by default, the first bump has been analyzed. What we want is to avoid the analysis of this bump, so we will change the condition on the branch to be sure that the other branch will be analyzed. So we will set the 0 flag to the correct value at this instruction, and we will analyze the other branch. Let's do it. So we edit the configuration file of BinCAT. We set the flag with the right value, relaunch the analysis, and now we can see that the first bump has been diffused. Let's continue. There is a second bump here, so we will do the same. We will set for this instruction, we will change the value of the 0 flag to go into the other branch. The second bomb has been diffused, but there is a third one. To speed up the demo, I will provide to BinCAT the complete configuration to avoid all the bombs. It's a text file. We will see it later more in detail. We will run the analysis. And this time we see that the entire path from the entry point until the last instruction of the program has been analyzed. We just need to see what has been computed by BinCAT to get the decrypted flag. So we edit the memory. Actually, the flag was inside the heap, and this is the decrypted flag. So let's continue with a second demo. This time we analyze the key enemy. This program takes several arguments: the company name, the department name, the name of the user, and the license. If you provide with a wrong serial number, then it will print out invalid serial, wrong serial. And if the license is correct, it will print out thank you for registering. How it works internally. So this is the C file. First, every argument is controlled for integrity. Then the result of the CRC of the company and the name of the user are multiplied together. Then the result is stored into a sprintf in a buffer together with other arguments. The result buffer is then hashed, encoded as an hexadecimal string, which is actually compared with the correct license. This time for BinCAT, we will need to set the configuration file to add a value for each argument on the program on the command line. So let's do it. So we will generate a new configuration file. It contains a lot of pre-computed information. For instance, as our the executable is an ELF, we need the GDT for Linux. And here there is a special section for the initial state of the memory. By default, everything is set to an unknown value, which is the meaning of this question mark. This is here that where we will set a value for each argument. So here we do it, and at the end we have an import list which enables BinCAT to know what kind of external functions are called. This is needed by BinCAT because it has to mimic the behavior of each library function, because the program under analysis is never executed. So we save the configuration. Rerun the analysis. Again, it's showing red here. And if we edit the memory for the entry point, you can see that it contains the value for argc and every program argument. And in particular, we provided the wrong license number. If we go inside the function that computes the hash, then you can see here that the sprintf has been mimicked. So we get the result of in another buffer. And we have more. We have inferred some type information based on the signature of sprintf, which means that the first argument, which is the destination buffer, is of type string. Same for the source buffer, the format string, and now EAX, which contains the result of the function, is of type int. Here we have an interrupt call to the function that prints either a wrong serial number or thank you for registering. By default, IDA is not able to compute such a target jump because it depends on the value of the register, but BinCAT is able to do so. So let's ask him to follow this indirect jump. Here you can see that it has followed the print function that print the invariant serial message, and also that printf has been stuck. This is the third and last demo. What I want to show you is that in that demo is that every analysis in BinCAT is done in parallel. So we will add, by default, there is always a value analysis, but you can add some more sophisticated analysis. So here we add a taint value, which means that we want to track the impact of an input over the program. We will track the company. So for that, we will taint it. And this time we provide a correct license number. So we taint a company. We launch the analysis. And when it's done, you can see that the company in the memory, it's now in green, which means that it has been tainted. It will be the case for every impacted data on them and by the company. Also, in the graph view, you can see that every instruction that manipulates data, tainted data, is also in green. In the function that computes the key, you can see that this block of instruction is in green because it computes the string length of the company. Also, as we compute the TRC of the company, the result is EX, and I'm not sure you can see it, but here this is in yellow because only some bits in the nibble are tainted. Also, the taint analysis also work for arithmetic operations. You can see both the taint effect and the value of the computation of the arithmetic operation. Next, we enter the hash function. You can see the result is tainted because the company is tainted, of course. And every loop can be unfolded, so you can see step by step how the loop are computed. So here you will see that every byte is in the formatting loop is changed both in value and in taint. If we go to the end of the program, you have this indirect jump to the print function, and now this time you can see that we take the function, we analyze the function that prints thank you for registering, and it is also tainted. So how it works internally? You've seen that on the one side you have IDA and this plugin mechanism. So we have a plugin in Python for IDA. On the other side, we have a complete standalone executable, which is written in OCaml, and the communication between the two modules are done with text files. This is mainly due to the fact that IDA doesn't manage well DLL for 64 architectures. So the main algorithm inside BinCAT is a reconstruction of the control flow graph. Suppose that we have already reconstructed this control flow graph. A state in this graph contains everything we have computed so far. For instance, we have the instruction pointer, the value of the register, the flags inside the memory Also in green when it's tainted or not, the type that some register may have, and so on. And for the first, the initialized state has been computed from the information we get into the inside the configuration file. So suppose that the current state to explore is state 4. We extract some information inside this state that are useful for the decoder, mainly the instruction pointer and something about the segment for x86. The decoder will pick up the native instruction, translate it into a state of statements in our intermediate language. For instance, when you increment a register, the register will be incremented by 1, but also you have an update of every flag. We generate a new state, which is a copy of the current state, and we will update the state with the set of statements that we have. So of course we update the instruction pointer, the value of the registers. Here you can see that when there is an overflow, then the taint is also propagated to this overflow. We update the flag and the memory. And then if the state is new, then it is added to the list of states that has to be explored. Of course, a legitimate question is, how can this algorithm terminate in case of you have to analyze a loop? Well, this is because it's based on a theory which is called Tract Interpretation. In this theory, the states that you have just seen are actually a set of value, which means whenever you have seen 0, it means that it is the interval which contains only the 0 value. And also, each set is actually an element of a mathematical structure called complete lattice. It means that the elements, so the sets, are ordered. For the interval, it means that, for instance, it's the subset order, which means that here you say that this one is less than this one because this one contains this one. You have a second property, which is that there always exists a list of bounds, which means for intervals that for any pair of intervals, you can find another interval that contains this one, and which is the minimal one that contains both. Sorry. Also, you don't compute how you want the operation over these elements. They have to be an over approximation of the real one. That means that they always need to contain the exact results. For instance, in our inc instruction, this is correct. If your register is inside this interval, then of course, after adding 1, it has to be inside this interval, okay? This one is also correct, while not very precise, but this one is not correct. Okay, for instance, if the real value in the real execution of the program is equal to 1, then the result can be 4. With all these properties, and also there is a special operator I don't want to talk here in detail, but if you have questions after, we can discuss about it. There is a special operator to over-approximate every loop, which is called widening. It enables to over-approximate loops in a finite amount of time. Then you will get this famous theorem by a couple, but everybody only reminds the man in the couple. I don't know why, but there were two to do it. So the first property is that the fixed point of the control flow graphs that we have computed can be do it in a finite amount of time, and it contains all possible traces that can be that are I mean, it contains all real execution trace of your program. And so we have a lattice for every property that we have to compute. So for value, for taint, for type, for the heap modeling, for the stack overflow detection, every time we have to compute a new property, we add a lattice, and so which makes easily communicate the analysis. And I think so. I hope you enjoyed this presentation because we like building new analysis with it. It's some kind of our baby that's still growing on this yellow part. So what we want to make it grow, even what we want to add more decoder here. We are currently working on MIPS decoder. We would like to have a github plugin, but there are not many volunteers for that inside the team because nobody really likes Java. And the more challenging part is inside this one. What we want to plan is to add a lattice to recover the class hierarchy inside C++ binary. And that's it. Thank you for your attention.